Here's problem 4 of the March 2011 exam 2. So it says 2 infinite charge sheets are arranged at x equals 0 and x equals plus 3 centimeters as shown. Plot the x component of the electric field and the electric potential along the x-axis over the range -4 to plus 6 centimeters. The electric potential is defined to be 0 at x equals 0, and a positive value for Ex means that the field points to the right. Okay, so we have a positive charge sheet here and a negative charge sheet here, and the first thing we need to do is plot the electric field at different x positions. So this is the x component of the electric field. So there are a couple ways to think about this. One is to remember that these two oppositely charged sheets are basically just a capacitor, and the field outside a capacitor, the electric field is 0 on the outside of the capacitor, and on the inside it points to the negative sheet and has a magnitude of charge density over epsilon naught. We could also have just gotten that from remembering that the electric field due to a single charge sheet, so ignore this one. For the positive charge sheet has an electric field that points away from the sheet, so this is the direction that a positive test charge would move in. If we just put it there, it would be repelled from the positive sheet. And this has a magnitude of, so this is E plus, so just from the positive charge sheet. This has a magnitude of the charge density over 2 epsilon naught. And then from the negative charge sheet, we have an electric field which points toward the sheet. So at any point in space, you have an electric field vector which points toward this sheet and has a magnitude of sigma over 2 epsilon naught also. This is, in this case, sigma is just a negative number. Okay, so outside, on this side of the sheet, we have our electric field from the negative sheet pointing this way. We have our electric field from the positive sheet pointing this way, and those cancel. Same over here. We have the field due to the positive sheet pointing this way. We have the field due to the negative sheet pointing this way, and they cancel here. And so you have these on the inside. You're pointing still away from this sheet and toward this sheet, and these 2 sigma over 2 epsilon naught pieces add up to this field inside the capacitor, field between the 2 plates. So if we want to plot that, then on this graph we have 0 field outside the sheets, so from -4 to 0 and from 3 to positive 6. So this whole range we have a 0 electric field. But then between the plates, so between 0 to 3 centimeters, we have a field in the positive x direction, which he says means that we have a positive value for Ex of a constant value. And that constant value is sigma over epsilon naught. Okay? So now we want to plot the potential between the sheets. And the thing that he gives us about the potential is that the electric potential is defined to be 0 at x equals 0. So electric potential, you could always add some constant to it. So you need to define it to be 0 at some point. And he gives that point at x equals 0. So you know that it's going to be 0 here. So there are a couple of ways to think about this to get from electric field to potential. One is that we know that the electric field is the negative gradient of the potential. So we need to plot something down here whose negative gradient or negative slope at any point gives us this plot. So it would give us a constant, a positive constant in here, and 0 out here. So at these points where it's 0 out here, if the electric field is 0, then the gradient of the potential is 0, which means that the potential is a constant. So we know that in this area out here, we're going to have some constant, and in this area here, we also have a constant. And then in between, we have something who the negative slope gives us a positive constant. So if the negative slope is a positive number and a positive constant, we have something that's linear and decreasing. So if it's decreasing like this, then the slope is negative, and the negative slope is a positive constant. So constant, linear decrease, and constant out here. So since it's defined at this point to be 0, then our constant on this side is 0. So constant, linear slope, and then constant again on this side. Okay, so that was kind of the math, a little bit more mathy way of thinking about it in terms of a gradient. Another way would have been that, the equivalent way is that to go from electric field to potential, the potential was the integral of the electric field dot dl. So if we take a charge and we move it this way, we are moving some vector dl. The electric field points in that direction also. And so out here, the electric field's 0, so we get 0, 0, 0 for this dot product. Then once we get inside here, electric field dot dl is some constant. And so as we move this way, we keep adding at some constant rate to our integral. So that gives us this constant increase down here in magnitude. The other way, the easiest way to think about it is a not math way, in my opinion, and that's what would happen if you put a positive charge somewhere in this electric field, and then we want to draw this kind of landscape down here, which would give us the same result. So we kind of imagine that we have a positive charge, we could put it on this hill, and it would fall in this direction if we put it here. And that's the case, that if we put a positive charge at the same point in this electric field, it would be pushed to the right also. But out here, there's no field, and it wouldn't go anywhere. Out here, there's no field, and it wouldn't go anywhere. So we know that down at these points where there's no field, we have to have a constant. And in here, we would have to have something that would constantly accelerate. So we would have a linear slope. Okay, so the next two parts of this problem are pretty similar. But now what you do is you add some more plates. So what that means that you can do is just take your answer from the previous section where you had this constant electric field between the two plates and add a new electric field due to these plates to it. So this is the superposition idea, where you can just, the total field is just the field due to all of the individual charges added up. So we knew that what we used to have was an electric field between the plates of charge density over epsilon naught, and that was in the positive x direction. And so now we get this extra field due to the same sort of thing in between these plates, where we have a new electric field added. That's E, let's call it E2, is the new charge density over epsilon naught, and that's still in the x direction since it points to the negative side. So just always remember, it's the way that a positive test charge would go. So if we plotted electric field, out here we're still outside of both of these two capacitor plates, and the fields due to each of those plates, each of these 4 plates, add up to 0 in this region. So we know that our electric field is 0 from here to here and 0 from here to here. Now what we need to do is find the electric field in here. So in here, the electric field due to these 2 plates is 0. So outside of these 2 plates, the electric field is 0. So right here, we're still between these outer 2 plates, and our electric field is what we found in the first problem. So sigma of these 2 plates, the surface charge density of these 2 plates over epsilon naught. So it's some sigma 1 over epsilon naught value from here to here and from here to here. And then on the inside, we have an additional sigma 2 over epsilon naught added to that. So it goes up some amount there. And so this value right here is sigma 1 plus sigma 2 over epsilon naught. Okay, the potential is the same sort of argument as last time. So we need to have something that's a constant when the electric field is 0. So it'll be a constant for all of this area and a constant for all this area, and it's still defined at 0 at this point. So we know that everything to the left is a constant, because its derivative has to give us 0. And the same out here. But in between, at all of these points, we have a positive electric field in the positive x direction. And so these are going to, that means that just like in this last problem where we had a positive electric field meant a downward slope like this, we have the same thing where the slope will increase and become more steep the larger electric field we have. So we have something that goes down, and then during this part with the high electric field it goes down sharply, and it goes down some more, and we have another constant out here. So where the field's back to 0. So in case I didn't draw that clearly, this slope and this slope are the same, and then this slope in the center where the electric field is large is it's a large negative slope.